This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 166. Before we get started, I'd like to mention that the Tower S RPM version 24 will be released next week on November 1st. The Tower S team will also have a huddle in the Slack channel tomorrow at 2 to 3 p.m. Eastern Time. So if you're interested in everything that is part of Tower S RPM version 24, please look for further information on that and consider joining our Slack channel. With that, we will move on to today's presentation, which is predicting pyrocumulus or pyroCb events through remote sensing resources in support of the National Weather Service and firefighting agencies. I'm glad to have Arunas Kuchowskis and Andy Lambert from the Naval Research Laboratory. Our facilitator is Ben Bartos, Fire Weather Program Manager from Alaska Region's Environmental and Scientific Services Division. Just a few reminders, as you just heard, this session is being recorded. There will be an opportunity for Q&A after the presentation. We particularly encourage participation from the field offices and regional headquarters. Post your questions in the chat and we will field them in the order they are asked. Also, if you have not signed in with your full name, please note your full name when asking a question in the chat. We are always looking for future presenters. Please contact our Tower S team, particularly Kashad Bowman and Emily Maddox. The training team can help create training materials that may be unavailable or point you to materials you may be unaware of. Ross Van Til can help with that. I'd like to thank our Tower S team, particularly Kashad and Emily, the Office of the Chief Learning Officer, the GOZAR JPSS program, our facilitator, and all of you for being with us today. Without further ado, let me introduce Arunas, who is a research satellite meteorologist in the atmospheric properties and effects section for the Marine Meteorology Division at the Naval Research Laboratory in Monterey, California. His research focuses on remote sensing of aerosols from wildfire outbreaks over Western North America and Saharan dust outbreaks over Northwest Africa. Since 2015, Arunas has been the principal investigator on NOAA-sponsored projects that investigates the skill of NewCaps, an algorithm that profiles convective phenomenology such as pyroCb and hot desert storms. He's been involved in training forecasters and firefighters at the NWS and forestry agencies. His co-presenter is Andy Lambert, who received his undergraduate degree in atmospheric sciences from the University of Utah. He continued on at Utah to obtain his master's, studying the impact of expanding agriculture on dust trends in the United States. And he began working at NRL-Monterey soon after graduation, where he works in software development, web development, and a variety of aerosol-related resources. Recently, Andy has relocated from Monterey to Salt Lake City as a remote employee. Arunas and Andy, we're glad to have you at the Satellite Book Club today.
Well, thank you, Jordan. I appreciate that. Can everyone hear me? I just want to make sure I have a sound check. Hello?
We can hear you.
Yep. Okay, good. Thank you. Okay. Thank you, Jordan. I appreciate the intro. And thank you for inviting us to the Satellite Book Club series. I'm very glad to see a huge participation in this just by looking at some of the members in the chat group. I am assuming most of you are familiar with both NewCaps as well as satellite applications in fire weather. I've noticed that previous seminars covered one or the other. We are funded by NOAA Joint Polar Satellite Systems, or JPSS, to provide a resource in predicting pyroCbs within 3 to 6 hours of onset. We presented our project in several conferences and workshops, both in-house and to the global community. We plan to use much of today's presentation toward the upcoming AGU and AMS conferences as well, if you are planning to attend those as well. Our team consists of myself, Dave Peterson, who is our primary SME in everything fire weather. James Campbell is our local program manager. We also have Andy Lambert, who will present with me much of today's material, and Lance Wilson. Both are contracted to NRL in the design and testing of our prototype. There. So looking at this figure, for those not that familiar with pyroCb, here's a great illustration on the left side of a creek fire event that occurred in 2020. We labeled the parts of this feature. As shown, the pyroCb structure is very similar to that of a high-base thunderstorm, with the exception that it forms convectively off of a wildfire instead of moisture. Note the initial smoky updraft that then mixes with mid-level moisture and can reach the stratosphere as both a moisture and smoke-filled cloud, as in this case. Although there is often a well-defined downburst, there is typically little rain that falls out of this plume. But lightning is a common feature, which can then, of course, create more wildfires downstream. Erratic activity, although rare, can also occur. The bullets on the right highlight the hazardous aspects associated with the pyroCb, with the firefighting up at the top, aviation hazards, and then a global smoke transport. And of course, there are algorithms and sensors that deal with that, and that's a hot topic in today's research. And then at the bottom are climatic impacts, namely that this smoke is very similar to volcanic eruptions and can affect the Earth's radiative balance, just like volcanoes can. In our research, we define and collect pyroCbs as a fire-generated cloud top that reaches 11 microns with a brightness temperature of -40 degrees in the atmosphere. Dave Peterson is in the process of publishing a very complete collection of global pyroCbs since 2013. And for those of you interested, that's just an advertisement if you do work in pyroCb territory. We see here in this figure various stages and developments of the pyroQ that doesn't quite reach -40. That's shown by this red line. And these are the first two columns that you see. And then, of course, you get the small and large pyroCbs above that level. As I discussed earlier, we are only focusing on the right two columns. So these are the people whom we're serving. In this figure, they seem well-equipped and well-numbered in battling any wildfire. But as most of us know, tragedy often can play a role where a group encounters unexpected flare-ups, rogue winds that can then surround them and even kill them mercilessly. I think most of us now realize that pyroCbs, once an unknown or rare entity in our studies, occurs much more often and plays a major role in generating these dangerous firefighting conditions. So our job at NRL is to assist in mitigating these occurrences using novel approaches with environmental resources or combinations thereof. Our designated user agencies are listed on the left, and then the user needs are described on the right. And our project is geared toward providing operational support to the wildfire firefighting community. Most of our region spans Western North America, including Western CONUS, Canada, where of course this year our efforts have intensified thanks to the very active fire season that they had. And we also cover all of Alaska. We have a prototype that is just about ready to be demonstrated and tested. We have developed some unique capabilities that we'll present a little later on. And we're interested in continuing collaboration with NOAA with the goal of making this an operational product in the future. So this slide shows a quick start of new caps that we apply. You see on the left is a figure over CONUS where NOAA 20 overpass laid down a swath of measurements converted to dots that researchers and operational weather forecasters can select and view. We can only apply, or I should say, we only apply the cloud-cleared green dots. In other words, where both the IR and microwave sounders are available in our prototype. As shown in the right panel, we apply for both the individual SKU-T profiles, and then at the bottom you see the derived stability and moisture parameters in that panel. As with other applications in convective environments, NuCaps performs reasonably well in these convective pyroCb events. These are diagrams that depict our flowchart of processes within the pyroCb early warning capability that eventually turn into project deliverables. So on the left panel, you see NRL developed an approach consisting of 100-kilometer radius pink circles surrounding the clusters of active wildfires, or the dark pink dots that you see throughout all of California. This was obviously a very active time period in that region. As shown by the bullets immediately above, this step consists of identifying individual wildfires which apply the 10-minute GOES ABI fire product. In this panel, you see a display of a NOAA 20 overpass from which NuCaps data are collected. Inside that red circle are embedded NuCaps dots, or I should say fire dots, that surround the particular wildfire region. The NuCaps green dots are visible as well, and that's what we use to profile that particular wildfire event. This zoom view helps to view the surrounding NuCaps profile around the wildfire cluster. NuCaps data are collected from the NOAA 20 during the early local times. So to the immediate upper right inset are a collection of SKU-T plots to the immediate within that red circle. And there are about 4 or 5 plots there that you see. So it gives the forecasters and research a general state of the atmosphere within pre-convective pyroCb conditions. As shown in the bullets above, the products is based on NuCaps-derived thermodynamic variables. There is a variation amongst the plots, but from a forecaster's perspective, one can develop somewhat of a consensus surrounding that wildfire. And finally, the figure, the right panel, contains 6-hour probability circles of pyroCb development. As shown in the legend in the upper right, the red circle poses the highest risk for pyroCb development that you see in that figure. Of note, we're only using NOAA 20 for now. This plot was taken from a FireX experiment back in 2019. On the left is a pyroCb development and associated research aircraft flying through that region during the late afternoon. On the right is the corresponding Spokane, Washington Rayward-Zon that was perfectly timed with the eruption. The labels within the SKU-T indicate the various microphysics and levels across the sounding and into the cloud. This represents what could be considered the classic sounding that would then be useful in comparing how NuCaps responds to these. This is a fairly complete collection of pyroCb activity on a global scale, going from 2013 to current time. Obviously, the orange column is just a striking example of this year's pyroCb events, mostly being dominant across all of Canada. And with this, I will pass the baton over to Andy to describe more of the algorithm development and testing that we're applying. Andy, you can take it away.
Okay, thanks, Arunas. Apologies for my voice today. I'm battling a cold, but I'll do my best here. So this slide here puts the cart before the horse a little bit with the figure that we're showing on the right. But we thought it was a good idea to include here because it gives some context to how our model testing and development compares to what we understand conceptually and climatologically about pyroCb development. So that figure on the left shows the pyroCb ingredients overlaid onto the picture there. And it demonstrates that you need a hot, intense fire at the surface with a near dry adiabatic lapse rate. And as you move up into the atmosphere, into the mid-levels, it requires mid-level moisture and some potential instability. And we juxtapose that with the figure on the right there, which actually shows relative feature importance between the parameters that we're using as inputs for our model. So we derived 7 meteorological parameters from the NUCAPS data. Those are the parameters labeled there on the y-axis. And according to our testing, as we were building the model, we could gather information on the relative importance and how predictive each feature was towards predicting pyroCb events. At the top there, you see the potential instability is the most predictive or most useful in predicting pyroCb events, followed by lapse rate, precipitable water, SIN, and vapor pressure deficit. CAPE and lifted condensation level are at the bottom there, and you'll see later that we ended up not including those 2 parameters in our model as they were the least important. The remaining parameters that show a high level of prediction do compare really well with what we understand conceptually as important ingredients to pyroCb development. Next slide, please. So every machine learning project will start with building the training data set. In this case, we're trying to predict a binary event. It's either yes, a pyroCb is going to occur, or no, a pyroCb will not occur. And so we developed the 2 inventories or databases for the yes and no cases. So for the yes side, as Arunas mentioned, Dave Peterson and NRL in general has developed a pyroCb inventory, which is very comprehensive and will be released soon. We used that to sample our yes cases, and we gathered the NUCAPS profiles around those cases. I won't dig into the filtering too much, but they're listed in these tables here. I will say that we looked at the profiles within 100 kilometers and within 6 hours leading up to the pyroCb events. The distribution spatially of those profiles for 2020 through 2022, which is the years that we're sampling here, those are shown on the map below, with the shape indicating how many NUCAPS profiles we have available for each event. For the no cases, Arunas also mentioned our clustering algorithm. So we applied that to VIIRS fire data to get fire clusters for the years 2020 through 2022. And we gathered NUCAPS data around the fires that demonstrated similar intensities to known pyroCb events. And the filtering is very similar again to what we use for the yes case data sets, but we also add additional filters to make sure that we're sampling for fires that are similar to those that have produced pyroCbs. Again, the distribution of those cases and those profiles is shown in the map below for 2020 through 2022. Next slide, please. That gives us 726 total yes profiles. So 726 NUCAPS profiles that are near in proximity to the pyroCb events. And for the no cases, we end up with 561 profiles. If you take those and you just plot them onto skew T's, all of them together, in this case, we separated them according to elevation, low, mid, and high elevation, because in many cases, the meteorological characteristics and environment that are required for pyroCb events may differ from elevation to elevation. However, in general, you can see that there is a difference in the profile pattern that we see for the yes cases compared to the no cases. And that specifically would be this inverted V profile where you have dry, dry air near the surface following a near dry adiabatic lapse rate and potential instability and moisture at the mid levels. You can see that in the yes cases, whereas the no cases don't really demonstrate that pattern and are overall more varied in their patterns. Next slide, please. So now we can move on to the initial testing and construction of the logistic regression model. So that is the model we're using is logistic regression. It's very good for binary classification and prediction. In this case, it's very useful in that it outputs a probability between 0 and 1. So again, we used the years 2020 through 2022. We ended up determining that the inputs that we would use would be SIN, vapor pressure deficit, lapse rate, potential instability, and precipitable water. We took our training data set and split it 80-20 in order to build our model and test our model. And the results of that are shown in the confusion matrix on the left. I mentioned that the output is probabilities, but if you just round them to either a yes or no or a 0 and 1 prediction, then we get the confusion matrix to the left, where the top left box shows where an event was not predicted and it was not observed. The top right shows where an event was predicted but was not observed. The bottom left shows where it was not predicted but it was observed, and the bottom right shows where it was predicted and it was observed. So of course, the top left and the bottom right are the two boxes where the model gets it right. And good news for us, those numbers are very high relative to the other ones. And if you stick those into some skill scores, you get out some pretty good results where our model shows 73% accuracy, does a good job of detecting the events. And even though the false alarm rate is maybe a little bit higher than we would like, at least for this testing segment, the hide key skill score suggests that the model is more skillful than just a random forecast. Next slide, please. So Arunas mentioned prior to my part of this talk that Canada has really exploded literally in terms of fire and pyroCb development. And so we'll be covering how our model is responding to those fires in a near real-time demonstration. So these are probabilistic pyroCb forecasts. This is what is produced from our geolocated information processing system. It's called GeoIPS. It's something that NRL has recently developed and is still developing and improving. And we've been able to incorporate our new algorithm in there to demonstrate how this works in a near real-time environment. So in this case, we have many large, intense fires ongoing on May 4th in 2023 in the mid-afternoon. The logistic regression model that we've built gives a 64% probability for the circle and that arrow there. And just to kind of explain how to interpret these figures, the pink or magenta pixels are fires. Those are fire pixels as seen from GOES. And the circles are what our model is generating and producing as probability or threat scores for pyroCb events. The oranges indicate a 60 to 80% threat score. So you could see that it is doing, well, it is predicting a pyroCb event for that arrow there. Next slide, please. And what you see later on in the day is that that area and others nearby, in fact, produced a large pyroCb for the marked circle and some smaller pyroCbs or pyroQ for other circles. And again, it's a 60 to 80% probability. Some of the others that did not produce pyroCbs actually had lower probabilities. There may be some more text on here if you click next, I'm not sure. Yeah, so I hope that we can see that this model may be useful for things beyond just pyroCb prediction. It's a pyroconvection prediction. Really, it can point out hazardous firefighting conditions and also potential for high altitude smoke injection scenarios. If you hit next, there's a little bit more text. So there may be additional benefits beyond just the pyroCb prediction here. Perhaps this is a Haynes index replacement, or can lead us to something that can serve as a replacement for that. Next slide. So we have a really nice animation here that shows us this May 4th event and how our predictions evolve over time as the fires develop and as we gain new CAPS data. We start off with minimal fire activity, but as the fires grow, we have more fire clusters to make predictions for. And especially in the center of these figures here, you can see these higher probabilities ranging from 60 to 80, where the orange marks an intense pyroCb event there. So you can see in those circles where they are orange, the also orange pyroCb indicators start to pop up as well. So it does a good job here. Next slide, please. This is another event on July 8th through 9th in 2023. Again, we'll just use an arrow to point to one of these circles here that did produce a pyroCb. The probability that our model output for this event here was 73%. So you can see the pink fire pixels there with the smoke plume coming off and the orange at the top of that plume indicating those that are being marked as intense pyroCb. So we had a large pyroCb observed with other fires with small pyroCbs or pyroQ surrounding that. So for some of those other orange circles, we also saw some activity as well. Next slide. We're going a little bit more local here with the Creek Fire in California in 2020 on September 5th. This is an interesting case because the fire was very intense, but the meteorology was marginal. If you look at that in the context of the ingredients necessary for pyroCb development. So for our case in that circle with the Creek Fire pyroCb, our model output a probability of 45%, which is lower than some of those that we were looking at earlier. But it's a good time to remind everyone that the model that we've built does not include fire characteristics as inputs to the algorithm. It's all just those meteorological parameters that we've derived from the new CAPS data. So because the meteorology was more marginal, our probabilities showed up to be a little bit lower, but still a 45% is fairly substantial in the context of what's happening here. Next slide. I think it's a good idea to demonstrate how the model reacts in some of these more stable regimes. And the result is that it does well. This is June 3rd, 2023, where we actually have quite a few fires scattered around here that our algorithm has identified as something that we will produce probabilities for. And we can see that the probabilities range from quite low at 6% to 43% for most of these. So there were no pyroCbs observed this day, and our algorithm also did not really predict any to occur. So that is good news. Next slide. We'll show the same kind of thing, a stable regime in a loop here. So this is a stable synoptic regime in the wake of a mid-latitude cyclone, where we do have some decent fire activity, but our model is outputting probabilities that range from 20 to 22 to 21%. And again, there were no pyroCbs observed this day. So there are no false alarms here in the stable regime, and that's good news for the results of our model. Next slide. Oh, that's the end of my part. I will pass this off to Arunas to finish this up, and thanks for allowing me to speak to you today.
Thank you, Andy. That was great. And for the essence of time, I will keep these last two slides brief. So we're working with Mike Pavlonis, the NOAA program manager. There's a fire test bed that is starting up, and we hope to become a big part of that with our algorithm. And then you see the various components, the NOAA Fire Smoke Initiative, the Fire Weather Test Bed that I just mentioned, Smoke Modeling Team, Alaska Fire Weather, and then of course our IMET teams. And you can see there are a number of them, and we hope to increase that number as time goes on in terms of coordinating and having them test out our stuff. And finally, let me see if I can get to it. There we go. So these are the contacts. Dave Peterson is the primary one, and I am the more of the program little meteorology side, if you will. So we provided you a briefing how our project applies to NewCaps toward predicting the onset of pyroCbs using established climatology and a conceptual model. This slide you've seen a couple of times, and we follow distributions of thermoparameters, as I mentioned, in established climatology. And the big deal with us is that we are able to get near real-time pyroCb information. And then finally, this is the community that we're targeting. And we also have other agencies in terms of being able to demonstrate our prototype and receive feedback. And with that, I conclude this presentation. Thank you very much for listening.
All right, thanks, Arunas. This is Ben here for moderating the Q&A portion of this. So everybody, please stay on for hopefully some real good discussion on what this really cool project entails. First things first, before we get into that, as you see on the slide there, please join us next Thursday, November 7th, for the next iteration of this call. And with that, there'll also be a feedback form on this session that should get dropped into the chat here, a link to it. If you could please fill that out, always looking to see how these are and improve where we can. And I should say too, as you see on the screen there, the next session will discuss new updates and capabilities in the Tower S RPM version 24 Spotlight. With that, on to questions here. Arunas, we've already got a couple in the chat here. I'll start with the first one, and that is from Brian Curran. Curious as to why the -40°C threshold was selected for significant pyroCbs. This would be the homogeneous nucleation level, yes, but would you miss producing downbursts with cloud top temperatures warmer than -40°C?
That's a good question. To me, -40 has been a bit of an indicator in terms of the intensity of thunderstorms. I think a person who's better able to address this is online here, Dave Peterson, if you wanted to chime in and discuss, because I think you were part of the group that determined that particular level.
Hi all, yeah. So the pyroCb data set that we have that was built over the years uses that -40°C simply because that's the threshold we used based on projects that we were funded on, getting at the bigger pyroCbs at the time. But as you see with some of the tests we have, we're doing a pretty good job at predicting these bigger pyroCbs. And if a fire has a high probability of producing the larger pyroCbs, it likely has an even greater chance of producing the various levels of pyroQ that lead up to that. And you see that in some of those tests. So the fires that have a large chance of pyroCb, generally, many of them produce pyroQ, and the majority of them are plume-dominated type behavior. So you can also think of this as kind of almost an alternative to the instability part of the Haynes index. I'll just pause there.
Thanks, Dave.
All right, and Brian, if you're still on, please feel free to chime in to see if that effectively answers what you were asking. I'll pause for a sec to see if he does. All right, nothing heard, so moving on to the next question.
He did respond. He says, I think so. Thanks.
Oh, okay, great. Okay, yeah, he didn't all the way in the chat there. Okay, I'm a little higher up in the chat looking through questions right now. Thank you for that. So on to the next one for everybody. Have you tried to implement this methodology on model forecast analysis fields other than new caps? Is the next one.
So we actually we have two funded projects. One is using new caps. The other one is a broader scope. And again, Dave Peterson is heavily involved with that. He's the PI of that. And again, for specifics, Dave, if you can chime in on this one as well.
Yeah, so the current presentation you saw is basically how much can we squeeze out of NewCap's data alone, from the JPSS perspective. So, just using thermodynamic profiles derived from space, we can do a pretty good job at identifying which fires are going to produce deep pyroconvection. But as part of an NRL-funded project, we're expanding this to use NWP data as inputs, and so that allows us to incorporate other information such as wind speeds, dynamics, along with the thermo and also fire predictors. That's obviously far more complex, and so it hasn't gotten to the point of being able to demonstrate like this yet. But we are exploring both, and both projects are roughly running in parallel and end, this year at about the same time.
Thanks again.
All right, cool. That's good information for everybody to know. Thank you for answering that. And moving right along, we've got same question from two different folks here. Tim Schmidt and Frank Alsheimer are both wondering, in fast-changing environments, how might a finer spatial, let's say about 4 kilometer, and temporal about 60-minute profile, like geo exo sounder, for instance, help for this application?
Well, that's a very good question. So with the sophistication of the geo sensors right now that are currently in orbit, we're able to extract and actually help provide blending information, if you will, with the more, I would say, precise sounding information from the polar orbiting satellites, along with the geo sensors. That is something that we're only working with NewCap's data and VIIRS data right now, but down the road that would be a great funding opportunity for us. We're working with NOAA to see how we might be able to enhance our efforts, including getting more surface information and a lot of things that NewCaps would be very sketchy on, being that it is a coarse sounder. So that's my explanation on that question.
All right, thank you. And just to circle back real quick to the -40C threshold question, Dan dropped some further explanation in the chat there for anybody interested. And we've got a couple more good questions here. One from Andrew Heidendier. What would the higher temporal refresh offered by a GEO sounder, or would the higher temporal refresh offered by a GEO sounder add value to this application? So similar question to the one we just asked.
And it's a good question. We are actually working with that. We now that I think of it, so one of our team members, Lance Wilson, is actually looking to apply GOES with the NewCaps. So trying to provide something, say, for going forward in whatever the profiling that the NewCaps had. So that is part of our modeling development. I don't know if Lance is not on this call, but if either Andy or Dave want to chime in on that answer. Well, I guess not. Okay, that's as far as I go with that.
No worries. And then we've got one from a fellow IMET here, Derek Williams. Would like to know, does the NRL have an archive for this project? It would be great to look at past fires with known pyroCb formation for general assessment.
So as I mentioned earlier in the talk, we are actually, Dave Peterson is actually in the process of putting out the comprehensive pyroCb catalog, if you will, dating back to, from what I remember, 2013. I could be wrong, it could be earlier than that. And again, that's about to be published and will serve as an incredible resource, I think, in being able to do research work on a pretty comprehensive set of pyroCbs. And Dave, again, if you want to elaborate on any of that.
Yeah, so that's a multi-year effort at NRL that goes back decades now. The actual inventory does start in 2013, as Ernest mentioned. It covers the globe, and it builds off of the comment in the chat that Dan Lindsay has about setting that -40 threshold. So, you know, we needed a criterion to distinguish what was actually going to be archived. It's very hard to archive every fire that produced pyroQ, but it is manageable to archive those that produced the deeper pyroconvection. So we're working very hard to get that out, and it will be released with the publication hopefully in the next few months here.
All right, thanks. And we got a couple minutes left here. So we'll try to squeeze in a couple more questions. We're still getting some really great ones in the chat. Hopefully we can get to most of them. We've got one from Mike Stavish. Were there any common themes identified in the false alarm events? And I actually had a similar question myself that I decided not to ask since we were already getting some good questions in the chat.
Andy, can you answer that? Because you've been working pretty extensively with the null cases.
Yeah, can you ask the question one more time?
Sure. It is, were there any common themes identified in the false alarm events?
Oh, yeah, I mean, that's that's something that we need to investigate more. We're in the process of picking out specific if cases where we're getting these false alarms, and we're investigating those on a case-by-case basis. So I would say perhaps the common theme that we're discovering so far is that the meteorological environment is perhaps slightly more unstable or moist or something like that than we would have initially expected when we're just looking at it from a map or something like that. So if you look at the NuCaps profiles themselves, they show more of those ingredients than we would initially expect. I think especially at the mid levels. But that's still something that we are currently working through and trying to identify.
Okay, cool. Thank you. And go for the one last one here from Mike Pavlonis before I pass it back to wrap this thing up. Do you have a sense for how much the environment matters relative to fire intensity?
So I can take that one. So it's often very much a trade-off. So we see situations where the environment is a key driver. If the environment is very favorable for deep convection, it often doesn't take a very intense fire to generate a pyroCb. But on the flip side, if you take the creek fire example, you know, in that case, the environment was only marginally favorable for deep convection, but you had an enormous fire, basically like a bomb going off. And so that additional heating was likely the force that allowed for such a deep event to occur, you know, when it otherwise wouldn't without the fire. So, you know, it's a trade-off between how favorable is the atmosphere versus how much fire heating do you have to contribute additional instability.
And I'd like to just enhance that by saying that Ben Bartos the facilitator in this mentioned in conversations that while working in Alaska, it's basically a heads up, all hands on deck whenever there is convection throughout that environment in terms of anticipating maybe a pyroCb event. So the IMEC community is very much prepared, a lot more sensitive, with a lot more sensitivity whenever a day like that occurs. So.
Yes, thank you for that, Arunas. That's what got me interested when we first connected with this project. It'd be awesome to have that heads up that we could be having a pyroCb event. But with that, Rob, see your question in there. We'll try to get it answered another way, and then I will pass it back here to wrap things up real quick since we are running out of time. Thank you.
Thank you so much, Ben. And I want to once again thank our presenters today, Arunas Kuchauskas and Andy Lambert, for that outstanding presentation. And thanks to everyone for the discussion. Really fantastic. Once again, as a reminder, the TowerS RPM version 24 is going to be released next week, November 1st. The TowerS team is going to have a huddle in the Slack channel tomorrow at 2 to 3 p.m. Eastern time. Please keep an eye out for that, or get in touch with John Evans and Emily Maddox. Their email addresses are there on the screen if you have any questions about the coming TowerS RPM. And we will be talking about the TowerS RPM version 24 next week at the Satellite Book Club, Thursday, November 2nd at 12 noon Eastern time. Emily and John are going to be with us, so I hope you'll join us for that. In the meantime, if you have any questions related to the configuration of satellite products, Kishad and Emily can help with that. And of course, you can always find us on the TowerS Slack channel. All right, with that, we'll wrap it up for today. Hope everybody is doing well. If you are on the East Coast, I hope you are enjoying, particularly the Mid-Atlantic, I hope you're enjoying the very pleasant fall weather. And I hope you'll join us again next week for the Satellite Book Club. Thanks again, everybody. Take care, and so long.